Capturing CO2 from the air can support net zero goals. But first of all, what is net zero? Net zero means that for every molecule of greenhouse gas we put into the air, we also take one out, making our net emission zero. We reach net zero when the amount we add is no more than the amount taken away.
Let's talk about direct air capture, DAC. Direct air capture plays an important and growing role in net zero pathway. So, what is DAC? Direct air capture technologies extract CO2 directly from the atmosphere. The CO2 can be permanently stored in deep geological formations, thereby achieving negative emissions or carbon removal, or it can be used, for example, in food processing or combined with hydrogen to produce synthetic fuels. Today, two technology approaches are being used to capture CO2 from the air: liquid and solid DAC. Liquid systems pass air through chemical solutions, for example, an hydroxide solution, which removes the CO2. The system reintegrates the chemicals back into the process by applying high temperature heat while returning the rest of the air to the environment. Solid DAC technology makes use of solid sorbent filters that chemically bind with CO2. When the filters are heated and placed under a vacuum, they release the concentrated CO2, which is then captured for storage or use.
In the IEA net zero emissions by 2050 scenario, DAC technologies capture more than 85 megatons of CO2 in 2030 and around 980 megatons of CO2 in 2050, requiring a large and accelerated scale-up from almost 0.01 megatons of CO2 today. DAC is a key part of the carbon removal portfolio. Carbon dioxide removal, CDR, is not an alternative to cutting emissions for an excuse for delaying action, but is part of comprehensive strategy for net zero, where emissions being released are ultimately balanced with emission removed.
Momentum for direct air capture is growing. DAC plants currently operate at a small scale, but with plans to grow. Currently, 18 DAC facilities are operating in Canada, Europe, and the United States. All but 2 of these facilities sell their CO2 for use. And the largest such plant, commissioned in Iceland in September 2021, is capturing 4,000 tons of CO2 every year for storage. The first large-scale DAC plant of up to 1 megaton of CO2 per year is in advanced development and is expected to be operating in the United States by the mid-2020s. Governments and industry are getting behind DAC. Since the start of 2020, governments have committed almost $4 billion in funding specifically for DAC development and deployment.
Costs are high today, but projected to fall. Capturing CO2 from the air is the most expensive application of carbon capture. The CO2 in the atmosphere is much more dilute than in, for example, flue gas from a power station or a cement plant. This contributes to DAC's higher energy needs and costs relative to these applications. Future capture cost estimates for DAC are wide-ranging and uncertain, reflecting the early stage of technology development, but are estimated at between $125 and $335 per ton of CO2 for a large-scale plant built today. With deployment and innovation, capture costs could fall to under $100 per ton of CO2. DAC costs are dependent on the capture technology, solid or liquid-based technologies, energy costs, price of heat and electricity, specific plant configuration, and financial assumptions. In locations with high renewable energy potential and using best available technologies for electricity and heat generation, DAC costs could fall below $100 per ton of CO2 by 2030.
Innovation is needed across the direct air capture value chain. DAC technologies require significant amounts of energy to be profitable. Today, DAC plants have been successfully operated in a range of climatic conditions in Europe and North America, but further testing is still needed in locations characterized, for instance, by extremely dry or humid climates or polluted air.
6 priorities for direct air capture deployment. DAC deployment must be accelerated for net zero. The net zero scenario requires the immediate and accelerated scale-up of DAC, calling for an average of 32 large-scale plants, 1 megatons per CO2 per year each, to be built each year between now and 2050. This will require increased public and private support to reduce costs, improve technologies, and build the market for DAC technologies. The IEA has identified 6 near-term priorities of DAC deployment aligned with the net zero goal. The first one is demonstrate DAC at a scale as a priority. The second one is foster innovation across the DAC value chain. The third one is to identify and develop CO2 storage. The fourth one is to develop internationally agreed approaches to DAC certifications and accounting. The fifth one would be assess the role of DAC and other CDR approaches in net zero strategies. And finally, the sixth one would be to build international cooperation for accelerated deployment.